All right, so how about this? What if we want to do something like we want to deal with some other bases? Like let's say we want to deal with an exponential function, for example, without a base e. So we'll call it a base a exponential function. What do we do? Okay, what we can always do if we have bases other than e, we can always write them in terms of natural logs, which makes it very convenient, right? So yeah, we know that we could write this. We could write this as if this is equal to y. We could write that as a logarithmic expression, right? A log is an exponent. So how would I write that?
Log a
Base a log of
y to the x.
y equals
Or y.
x, because a log is equal to or is an exponent, right? So the log always equals the exponent. Okay, but either way, it's oftentimes more convenient for us to just turn this into an expression involving or an equation involving natural logs. And so the trick is we can always write this as a base e log. This is equal to e to the natural log of a times x. Okay? And here's partly why that's the case, because we can, it all essentially comes back to this idea. The base a log of x, we could write as the natural log of x over the natural log of a. Okay, that's generally true. Right, and so what does this become over here then? If we want to write that expression, that would be like saying what?
ln y over ln.
Yeah, natural log y over natural log a equals x. And so now does it make sense, right? Now we've got, if I were to multiply each side by log a and then exponentiate both sides, base e, exponentiate both sides, don't I just get that? See what I'm saying? Okay. Does that make sense? Okay. So that's very useful, because then it allows us to do a bunch of things. So we could say, like, well, so for example, we could even come up with a bunch of new standard forms that really are unnecessary in a way. They're just based on this one simple relationship. But what would we get if we were to say, like, we want to figure out we want to write a general derivative rule for a to the u. What's that going to be? Well, keeping in mind that a to the u can just be written like this, what's the answer going to be?
U a negative u or 1 minus u.
So it'd be like saying the derivative of e to the natural log a times u. And what's the derivative of, what's the derivative of e to the u?
Just u times
E to the
the 1
u
minus
times u prime, right? Derivative of an exponential is itself. That's the weird one, right? See what I'm saying? Right, the derivative, what's this? What's the derivative with respect to x of e to the u?
It's just
E to the u prime, right? Because the derivative of e to the hand is e to the hand, right? Right? Okay, so then if we just go back, what are we going to get here? Well, I'm just taking the derivative of that, aren't I? Right? So really this is just equal to the derivative of e to the hand is e to the hand, only that's a u this time, right? See what I'm saying? We good? Okay. Oh. Yeah, okay. So then what's the derivative of hand? What's the derivative of hand, right? The derivative of e to the hand is just e to the hand. Now we have to take the derivative of hand. What's the derivative of natural log a times u? Let's do this different way. Let's try this way. Let's just rewrite this as, let's take this guy and let's just rewrite it. Let's rewrite that as e to the log a u. Just use chain rule. Okay, the derivative of e to the hand is just e to the hand. Okay, we good with that, right? Next layer in the chain, though, is what's inside the exponential? Well, it's this thing right here. What's the derivative of hand? Log a is a constant, isn't it? So what's the derivative of a constant times u? Well, no, constant times u.
Oh,
With respect to, I mean, isn't that just going to be the constant I just pulled out front, right? See what I'm saying? So we're just going to get a log a, and then the derivative of u is what? By definition, derivative of u with respect to x. U prime. Right? Does that make sense? Okay, so then what is that? Well, I could reverse this substitution. What is that whole thing right there?
that's
A to the u, right? So then I could write this whole thing as just natural log a times a to the u prime, right? And so that's how we can, that's our standard form. If we want to use that form, we can just write this as natural log a times a to the u prime, right? Is that completely necessary? I mean, it's nice to have. Is it a big deal? No, not really, because we could always just rewrite it as a base e exponential and natural log and do that instead, right? Does that make sense? Okay. All right, so what, okay, so let's try one of those. How about? Let's just do a sample problem. So what about if we had, what's the derivative with respect to x of, oh, let's do 2 to the 3x. So what's that gonna be? We're just following that pattern, right? What's a? What's u?
3x.
Okay, so what's the answer?
Line 2.
Natural log 2 times 3. Okay. Make sense? No big deal. Okay, but it's just kind of a shortcut, right? That's all it really is. Okay, so what about, let's do the other new standard form that would make sense. Once again, it's not necessary, but it's convenient. What about something like this? What if we want to do the derivative with respect to x of the base a log of u? Okay, so to derive this new standard form, let's write that in terms of stuff that we know. How would I rewrite that log using natural logs? Okay. So natural log u over natural log a, and what's that going to give me? What's natural log a? Is that a variable or a constant? That's a constant, right? So if I'm taking the derivative of a constant, I can pull that out front, can't I? Right? So I've got my 1 over natural log a times the derivative with respect to x of log u. Well, what's that? What's the derivative with respect to x of log u? What did we say that was?
It's not,
What is that again? You guys, you remember that one yet? You done enough practice with that one? What's the derivative with respect to x of log u?
u squared over u.
U prime over u. U prime over,
Oh,
Yeah,
yeah,
right.
I was looking at.
right, so it's 1 over u times u prime, so we just usually write it as u prime over u, right? Okay, and so then what do we get for our answer there? Well, I mean, we can just leave it like that. If we wanted to, this would be kind of crazy. Actually, no. That's it. We can't do anything else with it anyway because we lost our log u. Yeah, so that's our answer, right? So we can write this generally as u prime over natural log a times u. Okay? Make sense? Okay, let's try one of those. So if we wanted to do what's the derivative with respect to x of the base 10 log of, I'll be tricky here, of x cubed. What should we do before we even start this thing?
Change it to natural.
True, I mean, we could, but there's something else we can do here. If I have a log of x cubed, what can I do with the exponent?
Apply the base method.
Well, I'll just bring it out front, right? That's a property of logs, remember? So we could write that as the derivative with respect to x of 3 times the base 10 log of x.
You
Right.
have for the 10, this isn't like log 10 like standard. form.
It is, yeah. I mean, if you just write an log log, it implies base 10. Yeah, it's called a common log. And so then at this point, here's our standard form, right? I never, ever remember this standard form. I always just turn these into a ratio of natural logs, right? Which is essentially all you're doing, isn't it? Right, so this would just equal the derivative with respect to x of 3 times natural log x over natural log 10. Everybody agree? Right? And so then what do we get? Well, 3 over natural log 10 is a constant. What's the derivative with respect to x of log x? I mean, people just haven't done a lot of these assignments yet. I think this, I get it. People have been on trips and things. Jonathan's got it. You have this one, Jonathan. What is that? What's the derivative? What is it?
I don't know, e to the x.
Derivative with respect to x of log x. That's just 1 over x, right? Okay, so here, let's review those real quick. If we just go through them once, you guys remember them. So let's do this. What is if y equals natural log u, y prime equals what? What's the derivative with respect to x of log u?
U prime over u?
U prime over u, right? So if that's an x, it's just going to be x prime, which is 1 over x, just 1 over x, right? Okay, how about if y equals e to the u, what does y prime equal? Remember, the derivative of e to the u is just, that's the one that's the easiest one ever. It's just itself, right? That's really bizarre, but the value of the function also always equals the value of the derivative, which is for e to the x, which is pretty strange. Okay, so we just get e to the u times u prime, right? So literally, the derivative of e to the x is e to the x. Strange, but true, right? So then what do we get here? Well, I get, here's my constant, right? We always want to extract the constant. That makes things a lot easier. So we get 3 over natural log 10 times the derivative with respect to x of log x, which is just 1 over x, right? So we get 3 over natural log 10x. Okay. You can use that if you want to, but it just seems like it's a waste of brain cells to remember that one. It's so easy to just change it into a ratio of, right? You could use that if you want, but isn't that just easier, right? Just to write it that way. What do you think? I think it is. Okay, let's stare at that for a second. Okay, does that all make sense? All right, so what else? Anything else that comes out of that that's anything strange? Oh, this is kind of cool. I will show you I'll just mention something. Not that this is something that's a big deal for right now, but when you do more calculus, which you will, hopefully, right, all later on in college, when you do, there's a whole part of calculus. So here's kind of what your landscape looks like. So we learned the process of differential calculus, taking derivatives. We learned the important applications of differential calculus. We learned how to do related rates problems, right? We can take a dynamic situation and we can relate rates of change of different variables by taking derivatives, right? And at the end, we'll probably go back and I wouldn't mind just reviewing a couple, going through a problem each of all these things, so we tie it up at the end of the year so you'll remember it for next year. Optimization, right? We learned how to do optimization problems where we can take a function and we can find the important places on some function. And primarily we'll find the relative extrema, right? We can find the peaks and the valleys, the maximum and minimum values of some function on some domain where it's important to us to find that stuff. Or inflection points too, sometimes that's the point of diminishing returns in economics. And we'll go back and look at one of those too before the bitter end. But then really that's what we did. That's differential calculus, right? Derivatives, and you know, it's still a work in progress, but derivatives are easy. You just follow rules on derivatives. You can remember the rules, the derivatives are easy. Then we flipped over and did integral calculus, the concepts of integral calculus, right? And so we built that up from basic principles where we used limits, right? Where we looked at discrete, areas under curves using rectangles, and then we consolidated that into a shortcut, right? Into what we call integral calculus. So it's the fundamental theorem of calculus, right? So we can find areas under curves by just looking at antiderivatives over limits of integration, right? And of course, antiderivatives we also threw in there. Antiderivatives are just the inverse operations for derivatives, and that's harder than doing derivatives. But we got some practice with making U substitutions, which is sort of like the chain rule for antiderivatives, okay? And then now we're just adding other functions to the whole mix for both derivatives and integrals, right? Where we're going to kind of end up this year is I want to look at how to solve some ordinary differential equations using this new stuff. And this is a great place to stop, I think. What are some other topics that, we could have done something else instead of this, but to me this makes the most sense. So what you're going to look at next year then, like in second semester calculus, and I would recommend, honestly, probably just doing calculus from the beginning in college. It's just because you're going to get a little different look at it. When you're going away to college, you're all going to be taking hard classes. Calculus will be easy for you. It'll be a piece of cake. I mean, because you've done all the essential stuff for at least first semester calculus. Second semester, you would take integration a little further by looking at some different techniques of integration. What happens if U substitution doesn't work? So you'll presumably learn like integration by parts, integration by trig sub, just some stuff like that. It's not hard. It's really not hard using mixed fractions or what do they call that? Improper sums. There's just some techniques of integration where you can deal with some other oddball kinds of integrands that don't work using U substitution. And that's no big deal, you know, I mean, it's, you gotta kinda learn those techniques, but they're not hard. Then you would also, the next step would be, you would look at probably some solids of, some applications of integrals of surfaces and volumes, which is pretty cool stuff, and I've always enjoyed teaching it, but I don't know, I think this is more important. So you'll look at like how you could find the volumes of, say, solids of revolution, things you could turn on a lathe by picking the right kinds of cross sections and taking an integral that adds up the right kinds of volume shapes. You can add up those volumes. And so it just takes what we've done, definite integrals, over values of x, and we're gonna look at definite integrals involving, instead of just little pieces of x, we're looking at little pieces of volume. Okay, so it just extends all the stuff we've practiced into a slightly different, notice these all just kind of go off on side tangents, right? Okay, the other thing you'd look at after that is you'd start to look at the calculus of discrete sums, looking at some statistical stuff using calculus, and that's where you'll see this again, right? Here's an interesting limit involving E. So this is true. The limit as x approaches infinity of 1 plus 1 over x to the x is equal to, if I rewrote that as just having a common denominator, wouldn't that just be the limit of x plus 1 in the numerator over the common denominator x? So what's that going to be? What's that give you? Well, as x approaches infinity, this looks a little strange, right? This term is going to approach what?
Something very small.
Something very small. So we get a 1 plus in here, right? Well, this approaches infinity, it's indeterminate, right? Turns out that the answer is E. Okay? And so what that allows us to do is it allows us to take some things like if we were going to, let's say we're looking at some economics applications where we want to look at compounding interest, right? Here's the formula. This is the formula for compounding interest where, what's the number of n times annually, okay? So it looks like this. It's principal times 1 plus the interest rate written as a decimal over the number of compoundings taken to the n, okay? That's what happens. So that's looking at your yearly accumulated interest, once again, where R is the interest rate and N is the number of compoundings. So if you just compounded it annually, N would be 1, right? And so you would just end up with the principal times 1 plus R, right? So if the interest rate was 5, that makes sense, doesn't it? 0.05, right, 5%, you just get 1.05 times your principal and just multiply by 1.05, right? But the more times you compound, the better off it is for you, right, for the person who's investing the money. What if N were 2? Then we'd have to, we'd end up with 1 plus 0.05 divided by 2, right? So that's going to be 0.025 to the 2. Okay, that's going to be a little bit bigger than 1.05 times p to the 1. You get the idea? Okay, so then what happens here, if we want to write this, in terms of a continuous, what if we want to let the number of compoundings approach infinity, which is what we call continuously compounded interest, right? And that's how people do it, okay? How could we do this? Well, you could say that R over N is the same thing as the reciprocal of N over R, right? So we could write this as principal times 1 plus 1 over N over R, okay? And then we could say that instead of calling this an N, this is a little bizarre, but we could write that instead as n over r to the r. Okay, why would we do that? Everybody agree those are algebraically equivalent? Okay, if we're gonna let the number of compoundings approach infinity, then what does the value of n over r approach? Well, obviously, that's gonna approach infinity also, right? So let's just rename this. Just to make this simple, let's just let x equal n over r, right? As n approaches infinity, wouldn't x approach infinity also? You agree? Well, what's that then, right? Isn't this exactly like saying p times 1 plus 1 over x to the x as x approaches infinity, right? If we're going to let n go to infinity, we have to do this as a limit. We can't plug infinity in, right? You see where I'm going with this? So then a would equal the limit of this whole thing as x approaches infinity. And this whole part right here, let me make this whole part right here is just equal to e, isn't it? You see what I'm saying? Right, you get that? And so then this all ends up being e to the r, and if I want to do this year after year, I could just multiply by the number of years t, and I could call this a as a function of t, where t is the number of years, and it ends up being pert. You see how we get it? Okay, it just equals p times e to the r, and then we'll just include that t in there also, because we're just gonna do this. Isn't that amazing how, I mean, it all pops out then? So you just get pert, right? Because if I were to do this, think where that t comes in. I don't want to spend too much time on this, but I just want you to kind of see where this comes from. I think it's pretty cool. What if we wanted to do this for 3 successive years? Well, really all I'm doing is I'm doing it once, then I'm going to do it again and multiply, find that product, and then I'm going to do it again, right? Well, haven't I just done that? If I'm going to multiply it together 3 times, it's just cubed, isn't it? Well, if I take a power to a power, I multiply the exponents. So do you see why we can just multiply by t? Right? Because t is the number of times that we're going to perpetuate this process, because you're doing the same thing year after year, right? So there's pert. Okay, it all comes from this little limit, this little indeterminate form of a limit that we're adding. Okay. Right? So you'll see that again. I mean, you'll see that in college again. I don't expect this. You don't need to just remember this completely, but it always helps if you've seen it once, then you build a little bit of a framework, and next time you see it, you go, oh yeah, I remember talking about that, and it sticks better. Okay, so then I don't know if I'm even going to give you any. I'll give you like two derivative problems and 2 integral problems just to get the tiniest bit of practice on using those new standard forms. But here's the stuff that I really wanted to get to. Let's do something like this. Let's say, I'm just going to make one up. Okay, let's say that we want to model a growth problem, natural growth problem. This is really interesting because this is a very important topic. I mean, natural growth, population growth is huge, right? So let's say that we're going to look at bacteria in a dish or something. Okay, we want to come up with a growth model that's going to describe this. Let's say that we start off with 1,000 bacteria, and let's just say we're going to measure T in hours. And if we study this culture, we know that after 4 hours, the size of the bacteria population has doubled. Okay, does that make sense? Okay, so we've got some function. That's that color. So let's think about this, how I want to do that then. So, okay. That's a good way to show that. So, right. Okay, so I'm gonna do this slightly differently. I want to talk about this generally first. Okay, I got a better way to do this. Let's come up with a differential equation, just an equation that involves a derivative. Let's come up with a differential equation that's going to describe population growth. Okay, so let me ask you this: for a biological population, if Y stands for population, let's just say that Y, that's a function, and that's population as a function of time, let's say, okay? What is the rate of change of the population gonna have to be proportional to? Bacteria are multiplying, or lemmings are producing offspring, okay? Or humans are producing offspring.
Are we taking into consideration death?
Or not. Yeah. That changes, then we have to do, that's a different type of a curve, that's called a normal curve. It's different than the normal curve you're used to. But that's different, so you end up with a plateau. That makes things more complicated, we're not gonna do that for now. We're just looking at just regular old population growth, assuming unlimited resources, and then eventually the resources aren't unlimited and then you have problems. And at the end of the year, that's a really good discussion. We're almost getting to the end of the year, but I really would love to have that. I'd love to have that distribution I'd love to have that talk about Gaussian distributions and what that implies about finite resource extraction, because it's really profound and it's really scary.
We watched a video, we watched a video with the physics guy, it was like.
Oh, the old guy, Albert
Yeah.
Bartlett. Yeah,
I remember that from last year in physics, we watched it at the end of the year.
yeah.
What was it called? This is everything you need to know. or
Yeah, I've got it somewhere, but I love that video. I mean, he's just a crotchety old guy, but he just explains it in a way that is, I mean, he just kind of sums it all up. What's it gonna be? What's our differential equation gonna be, though? What is the rate of change of population have to be proportional to? This is nothing profound. But if I've got a population of 10 bacteria compared to a population of 100 bacteria, which one's gonna be adding population faster? How come?
Because there's more of them to reproduce.
Because there's more that can reproduce. So once again, what is the rate of change of the population necessarily proportional to?
Rate of reproduction.
Well, assuming the rate of reproduction, we're talking about apples and apples.
Current population.
The population, right? The more bacteria you have to multiply, the greater the rate at which it's gonna multiply. Wouldn't it make sense that the rate of population change has to be proportional to the population size? Right? What do you think that's gonna do? Just think about this qualitatively. If the rate of change of population growth is proportional to population size, as the population grows, what's gonna happen to the rate of change of the population?
Grow faster, so that.
What does that sound like to you?
Exponential.
That sounds like what we would say, man, it's growing exponentially. We always throw that word out, but it does sound that way, doesn't it? Okay, so here's the differential equation that would describe this then. The rate of change of population growth would be proportional to population, right? Everybody agree? Okay. K is just constant of proportionality. So let's solve a differential equation. Okay, I've actually showed you guys how to do this secretly, kind of sneakily, without telling you what I was doing. We can solve this differential equation by this is called the separable differential equation. We're just gonna get the y's on one side and the t's on the other side, right? So what's that look like? I'd end up with dy over y equals k dt, right? Everybody agree? Okay, if I separate the variables like that, that's all I've done, then how do I undo a derivative? Yeah, the integral or the antiderivative, right? So if I integrate both sides, I can pull the k out front. Okay, what is this one? What's the derivative of dy, or integral of dy over y? What's that one? It's a simple one of our new ones.
You don't know it? It was simple.
Isn't that
I know it's
just,
simple, but.
isn't that just the natural log? right?
Oh, yeah.
Natural log of the absolute value
Oh, yeah.
of y, right? And then over here, I'm just gonna get kt, and we'll lump a big constant together for the whole thing, right? Now, population is always non-negative, isn't it? So I don't need the absolute value bars, right? Okay. Tell me when everybody feels perfectly comfortable with that. Are we good? Okay. So let's solve this for y. What would I do to unlock a y from a natural log? What do I have to do to both sides? This goes back pre-calc. We reviewed this, but see, what are we gonna do?
Take E and then-
Yeah, we're gonna exponentiate both sides, right? If I take the base e exponential of both sides, you get that, right? Does that make sense? Okay, so then over here, that's gonna give us just a y. What do we get over here? Well, I'm gonna get an e to the kt plus c. Well, if I have a base to a sum, that's the same thing as writing it as the product of the separate exponents, right? So I could just write this as e to the c times e to the kt, right? Everybody agree? Okay. So then this is just some big constant. So let's just call that, I don't know, let's call it capital C, e to the kt, right? Well, what is that thing? Let's figure out what it is. This is really y as a function of t, isn't it? Right? So let's write it that way. So let's find out what's y of 0. If I plug 0 in, what do I get over here? C times e to the 0. What's anything to the 0?
1.
Ah, so what is c then?
It's 1. No.
It's
It's the population,
It's,
like, no, it's,
0. 1.
if Y is population, so it's zero for population,
What?
C would have to be
what is it?
nothing?
What?
I'm so confused. We said Y is population, right?
Mhm, it is.
So you're saying the population's zero.
Okay, no, I didn't say the population was 0.
Oh,
I
you
said at time 0.
Oh,
So what is that then?
so that's your starting population.
It's our initial population. Ah, okay. So C means something. C is the initial population, right?
Oh,
So look what this gives us then. We end up with y of t equals y naught times e to the kt. How about that? That's our simple model for population growth right there. This is so cool. The only thing that we did was we just made this simple logical assumption that the rate of change of population size was proportional to the population, right? Right? Population growth is proportional to population size. Total, I mean, that's makes sense. And we came up with that. It is exponential, right? Okay, so we've got this, let's write this slightly differently then. Let's write this involving p's instead of y's, because it makes sense. P is population, right? So P of t equals initial population times e to the kt. That's a good place to leave off. Okay. Isn't this kind of fun though? I love talking about this stuff because you can harness the stuff that we know to solve a differential equation and come up with something amazing. I mean, that's a really powerful tool, right? We could graph that and predict what a population growth is going to look like.
Hey, wait, Rube, something that way, it's still logged on.
That's okay.